Hello friends. In our last video, we have completed the examples on congruences. We will discuss again some more examples in that. The next example is if n is an odd integer, then prove that n into n square minus 1 is always divisible by 24. Here they are given n is an odd integer. We need to prove that n into n square minus 1 is always divisible by 24. Now, since n is odd, we can write n as a n is equal to 2k plus 1. Because n is odd number, we can write it as n is equal to 2k plus 1. So substitute in this, n into n square minus 1 is equal to 2k plus 1, n equal to 2k plus 1 into 2k plus 1 whole square minus 1. Then simplify this by using a plus b whole square formula. 2k plus 1 as it is 4k square plus 1 plus 4k minus 1 plus 1 minus 1 get cancels. Again, here in this bracket we have 4k square plus 4k. In that 4k you can take common, remaining k plus 1. So the number is 4k k plus 1 into, see it is 2k plus 1 is there, that how will adjust 2 will take as a common k plus 2. 2 into k plus 2 is 2k plus 4, but we have here 2k plus 1, so that plus 4 minus 3 will take, plus 4 minus 3 is 1. So therefore we are getting this number as a, and this 2 is a product in the product again. So what we can write this number as a 4k. See, n into n square minus 1 is equal to 4k into k plus 1 into 2 into k plus 2 minus 3 it is. So we will multiply this. This will multiply to both in this bracket. So getting 4 into 2, 8k plus 1 into k plus 2 minus 4 into 3, it is 12k into k plus 1. Now see the first term, 8 into k plus 1 into k plus 2. So it is k into k plus 1, k plus 2. It is a product of 3 consecutive numbers. So it should be divisible by 3 factorial, that is 6. So therefore, now k into k plus 1, k plus 2 is divisible by 3 factorial, that is 6. Therefore, 8 into k plus 1 into k plus 2 is divisible by 8 into 6. So it is not 4, it is a 48. It is divisible by 48, and 48 is divisible by 24. Here this is 8 into 4 is 48, so therefore this total number is divisible by 48, and 48 is divisible by 24. Hence by using transitivity again we can write 8 into this product is divisible by 24 also. Then next term in this, first term is divisible by 24 we got. In the second one, k into k plus 1 is a product of 2 consecutive numbers, again that is divisible by 2 factorial. 2 factorial is 2 here. So therefore k into k plus 1 is divisible by 2, and 12 into k plus 1 is divisible by 12 into 2, it is 24. As these both the terms are divisible by 24, hence the subtraction is also divisible by 24. Therefore n into n square plus 1, that is equal to 8k k plus 1 k plus 2 minus 12k k plus 1 is divisible by 24. Hence whenever n is an odd number, that time always n into n square minus 1 is divisible by 24. Next, the sixth example, prove that 13 to 2n plus 1 plus 9 to 2n plus 1 is divisible by 22. We don't know what is that number n, but 13 to 2n plus 1 plus 9 to 2n plus 1 is divisible by 22. See, for example, you substitute n equal to any number, any natural number you substitute here. N equal to 1 if I take, then 13 to 2n plus 1. 1 we have taken n equal to 1, 2 plus 1, 3. 13 to 3 plus 9 to 3. You calculate 13 to 3 plus 9 to 3, that is always divisible by 22 we are getting. Or else you may take 0. N equal to 0 if I take, then it is 13 to 1 plus 9 to 1. 13 to 1, 13. 13 plus 9 is 22 divisible by 22. For any number it always satisfies. So now see here, we will prove that in general. We will consider 13 to 2n plus 1 plus 9 to 2n plus 1, that is equal to 13 to 2n into 13 plus 9 to 2n into 9. Then 13 to 2n. 13 to 2n means 13 square whole raised to n. 13 square is 169. So it is 169 raised to n into 13 as it is. Plus similarly here 9 square raised to n. 9 square is 81. 81 raised to n into 9 as it is. Now we'll calculate for this. 169 is congruent to 15 mod 22. We have to divide this 169 by 22, so that we are getting the remainder as a 15. So therefore again by using property of that congruence, 169 raised to n is congruent to 15 raised to n mod 22. Now we have here 16 raised to n into 13. So 169 into n raised to n into 13 is congruent to 15 raised to n into 13 mod 22. That is equation 3. Also 81 you have to divide by 22. We are getting remainder as a 15. So 81 is congruent to 15 mod 22. Hence 81 raised to n is congruent to 15 raised to n mod 22. Therefore 81 raised to n into 9 is congruent to 15 raised to n into 9 mod 22. Now we'll add both these. This equation and this equation will add here. So writing 169 raised to n dot into 13 plus 81 raised to n into 9 is congruent to 15 raised to n into 13 plus 15 raised to n into 9 mod 22. So this is what 15 raised to n is common, 13 plus 9 is 22. So 15 raised to n into 22 mod 22. Now this is product 22 into this number is divisible by 22, hence it is congruent to 0 mod 22. Therefore this 22, the remainder we got is 0, hence we can say that 22 divides 169 raised to n into 13 plus 81 raised to n into 9. That is nothing but 13 raised to 2n plus 1 plus 9 raised to n plus 1 is divisible by 22. The next example, 9 raised to prove that 9 raised to n minus 8 raised to n minus 1 is divisible by 8. See, again I will put n equal to 1. 9 raised to 1, 9, minus 8 raised to 1, 8, 8 minus 9 minus 8, 1, 1 minus 1, 0, divisible by 8. Substitute 2, 9 square, 81, then 8 square, 64, minus 1, subtract. So 91 minus 64, minus 1, we are getting 24, that is divisible by 8. 8 3 is 24, and so on. So here we will prove that again in general. We will prove this by method of mathematical induction. We will use mathematical induction and we will prove this. So first we will take this P of n equal to 9 raised to n minus 8 raised to n minus 1. We have to prove that P of n is divisible by 8. So first we will check for n equal to 1, mathematical induction method. So we'll check n equal to 1 we will take. So we are getting that is 0 divisible by 8 as I told already. So now what we'll assume according to the induction hypothesis, we have to assume that it is true for n equal to k. We'll assume that the P of k is true here, that is P of k is equal to 9 raised to k minus 8 raised to k minus 1 is divisible by 8. Next we have to consider n plus 1. So n equal to k plus 1 will consider. What we have, as it is divisible by 8, we have considered that is 9 raised to k minus 8 raised to k minus 1 is equal to 8 into m for m belongs to z because it is divisible by 8 here. Now take n equal to k plus 1. So consider 9 raised to k plus 1, 8 raised to k plus 1 minus 1. So 9 raised to k plus 1 we can write 9 raised to k into 9 minus 8 raised to k plus 1 is 8 raised to k into 8 minus 1. Now see 9 raised to k is written as a 8m plus 8 raised to k plus 1 because by using this equation 1. In this equation 1, 9 raised to k is equal to these terms you have to take right side. So you're getting 8m plus 8 raised to k plus 1 into this 9 as it is minus 8 raised to k into 8 minus 1. So we'll simplify this. 8 9s are 72m plus 8 raised to k into 9 plus 9 minus 8 raised to k into 8 minus 1. Simplifying, we are getting 72m plus 8 raised to k. Says 8 raised to k into 9 minus 8 raised to k into 8, 1 we are getting. So 8 raised to k plus 8. Now 8 raised to k plus 8, 9m plus 1. See, this is because see here in this step what we have done, 8 raised to k as it is. Next 72m. From this 72m we have taken 8 as a common, remaining 9m. From this again 8 is common, remaining 1. So we got 8 into 9m plus 1. Again in these all the terms 8 is common. So in this first term remaining 8 raised to k minus 1 plus in this term it is remaining only 9m plus 1. So see it is 8 into any one number. So this entire product is divisible by 8 here because it is multiple of 8, which is multiple of 8 and hence it is divisible by 8. Therefore what we have here, this for n equal to k plus 1 also the statement holds. Hence by mathematical induction the P of n, that is 9 raised to n minus 8 raised to n minus 1 is divisible by 8. For every n it is true. For every natural number n the condition holds here. Now the next example, prove that 5 raised to 2n plus 2 minus 24n minus 25 is divisible by 576. Again, this result will prove by using the method of mathematical induction itself. So for we have considered P of n equal to 5 raised to 2n plus 2 minus 24n minus 25. Take n equal to 1. So 5 raised to 4 minus 24 minus 25 is equal to 5 raised to 4 is 625. 625 minus 49 is 576. 576 is divisible by 576. So therefore P of 1 is true here. Now let us assume that P of m is true. That is what 5 raised to 2m plus 2 minus 24m minus 25 is divisible 576. This we have to assume. Next we'll consider P of m plus 1, that is equal to 5 raised to 2 into m plus 1 plus 2 minus 24 into m plus 1 minus 25. Wherever n is there, you have to put m plus 1. So simplifying, it is 5 raised to 2m plus 2 into 5 square plus 2 is there. So it is 5 square minus 24m minus 24 minus 25, it is minus 49. So that is equal to, see, it is equal to 576k plus 24m plus 25. Why it is? Because see what you assume, this is 5 raised to 2m plus 2. Here we have assumed it is 5 raised to 2m plus 2 minus 24m minus 25 is divisible by 576. So therefore this product, this factor is equal to 576 into k, any one integer k, because it is divisible by 576. So therefore by using that equation, here we are getting 576k plus right side you have to take the terms 24m plus 25 into 25 square is 25 as it is minus 24m minus 49. Now again simplifying these terms, here we are getting this is P of m plus 1 is equal to 576 into 25k plus m plus 1. In this, again it is a multiple of 576, hence it should be divisible by 576 here. So therefore P of m plus 1 is also true, that is divisible by 576. Hence by mathematical induction, for every natural number n, this is 5 raised to 2n plus 2 minus 24n minus 25 is divisible by 576. So these are some examples I have quoted from properties of congruence. Next comes the Fermat's theorem, very important theorem. Either statement or state and prove, both they may ask. So statement is, if P is a prime number and A and P are relatively prime, this is what GCD of A and P is equal to 1 means they A and P are relatively prime to each other, then A raised to P minus 1 is congruent to 1 mod P. A and P must be relatively prime and P is a prime number. It is not necessarily A is a prime, but P is a prime, A and P are relatively prime, then always A raised to P minus 1 is congruent to A mod P, or A raised to P is congruent to A mod P. A raised to P minus 1 is congruent to 1 mod P, or A raised to P is congruent to A mod P. So we'll prove this result here. So here for this we will consider x1 plus x2 raised to P. We'll consider x1 and x2 p, any two numbers you have taken, then O raised to p is equal to, we have to expand this, writing x1 raised to p plus pc1 x1 raised to p minus 1 into x2 plus pc2 x1 raised to p minus 2 into x2 square and so on. Last term x2 raised to p we are getting. So that is x1 plus x2 raised to p is equal to x1 raised to p plus x2 raised to p plus this first term and last term we have taken here plus this is pc1 is p x1 raised to p minus 1 into x2 and so on. Here we are getting the simplified terms. Now that is what, now we'll consider, see this is what, here you may write, sorry, these terms instead of x1 and x2 you take as a1 a2 itself. Instead of writing x1 and x2, if you write a1 a2, a1 plus a2 raised to p, so everywhere wherever I said x1 and x2 you have to take as a1 and a2. So a1 plus a2 raised to p, left side a1 plus a2 raised to p is equal to a1 raised to p plus a2 raised to p plus the terms divisible by p. See, this is what, from this term, each term contains a p. Each after the first and second term you leave. Next from third term, every term is a multiple of p. P into, here also p into and so on. Last term also p into. So therefore what you will do, this is what, each term is a multiple of p here. Therefore, and this is a term divisible by p we are into. Then when you take congruence, a1 plus a2 raised to p is congruent to a1 raised to p plus a2 raised to p plus the term divisible by p means that here the term you are getting 0 plus 0 mod p. So therefore a1 plus a2 raised to p is equal to a1 raised to p is congruent to a1 raised to p plus a2 raised to p mod p. Therefore in general we can expand this. In general I will write for x1, or you may take for a1 also, no problem. Then x1 plus x2 plus so on up to xa, the terms you have taken up to a, xa raised to p is equal to x1 raised to p plus x2 raised to p plus and so on plus xa raised to p mod p here. Putting x1, x2, x3 so on up to xa is equal to 1. Every term in this, each term will put as a 1 itself. How many times you have added these terms? 1, 2, 3 so on up to a times. 1, 1, 1 up to a times you have to add. So left side what you are getting? A raised to p. The right side 1 raised to p 1, 1 raised to p 1. Again we are getting 1, 1, 1 so on up to again a times you are getting. So we are getting a raised to a plus a 1 plus 1 plus 1 means a, this sum is a raised to p is congruent to a mod p you are getting. That is our required result. See 1 plus 1 plus 1 a times you added, so a raised to p is congruent to a mod p. Then a raised to p is congruent to a mod p, we got this one result. Next what they have given, a and p are relatively prime to each other, that is the GCD of a and p is equal to 1. Therefore a raised to p is congruent to a mod p. That implies we can, as the GCD is 1, then we can divide, otherwise it is not possible. A raised to p minus 1 is congruent to 1 mod p, we can write. Next corollary, if p is any prime, then a raised to p is congruent to a mod p. See, for this Fermat's theorem we will see one example, numeric example I will quote here. If I have a prime number, as suppose if I take a prime number as a 7 is a prime number, then you choose a be any number. You may choose a as any number. For example, I may take 4. Now 7 is a prime number, then a we have taken as a 4. Then what is the 4 raised to 7? That you have to calculate. 4 raised to 7, or you may take 4 raised to 6. P minus 1 if you write directly, then 4 raised to 6 also you can write. And then is that congruent to 1 mod p, that you have to check. So 4 raised to 6, what we are getting? Yes, as you have taken the 7 as a prime number and a is equal to 4. So if you take here this p minus 1, a is congruent, a raised to p minus 1 is congruent to 1 mod p. So that is 1. 4 raised to 6 we are getting as a 4096. And if you divide that by 7, we are getting remainder as a 1 year. So therefore a raised to p minus 1 is congruent to 1 mod p. Like this, any number you can take and check here. Next, the corollary, if p is a prime number, then a raised to p is congruent to a mod p. See, in this itself we have proved. Up to this, nowhere we have used that a and p are relatively prime. So that by that is not this theorem itself. A raised to p is congruent to a mod p. So next, see here, we'll see some examples on that. If x is a prime number, then for all ab belongs to n, prove that a raised to p minus a b raised to p is congruent to a minus b mod p. If x is a in this step, if p is a prime number, it is not x, it is a p. If p is a prime number, then for all ab belongs to n, prove that a raised to p minus b raised to p is congruent to a minus b mod p. I see, given p is a prime number and ab belongs to n, a and b are any two natural numbers and p is a prime number, then by using this one, by using this corollary, we can write a raised to p is congruent to a mod p and b raised to p is congruent to b mod p. So by using the properties of congruence again, a raised to p minus b raised to p is congruent to a minus b mod p. That is the required. Then second example, if p is a prime and ab are relatively prime to p, then prove that a raised to p minus 1 minus b raised to p minus 1 is congruent to 0 mod p. Given here p is a prime number and what they are given, a and b are relatively prime to p, that is GCD of a and p is 1, and similarly GCD of b and p is also equal to 1. Then by using Fermat's theorem, as a and p are relatively prime, we can apply the Fermat's theorem here. By using Fermat's theorem, a raised to p minus 1 is congruent to 1 mod p. Similarly b raised to p minus 1 is congruent to 1 mod p. Now subtracting these both, a raised to p minus 1 minus b raised to p minus 1 is congruent to 0 mod p. That's the required. A raised to p minus 1 minus b raised to p minus 1 is congruent to 0 mod p here. Next example, prove that 5 raised to 10 minus 3 raised to 10 is divisible by 11. Now see here, this 11 is a prime number. 11 is a prime number, even 5 is a prime, 3 is a prime. So as they are prime numbers, these are relatively prime to 11. So you can apply the Fermat theorem here. 5 and 11 are relatively prime, 3 and 11 are relatively prime. So for separately 5 and 11 and 3 and 11 apply the Fermat theorem. So first we are getting 5 raised to 11 minus 1 is 10. 5 raised to 10 is congruent to 1 mod 11. See, I have written here. So that is not solved. 5 raised to 10, that is 5 raised to 11 minus 1 is 5 raised to 10 is congruent to 1 mod 11. And similarly 3 raised to 11 minus 1 is 10. 3 raised to 10 is congruent to 1 mod 11. So we are getting, subtracting both the equation, 5 raised to 10 minus 3 raised to 10 is congruent to 0 mod 11 we are getting. Yes, another example. Prove that n raised to 7 minus n is divisible by 42 for all n belongs to n. For all natural numbers n raised to 7 minus n is divisible by 42. So that is, for any n belongs to n, 7 is a prime number. As the 7 is a prime number, by Fermat's theorem, for any n belongs to n, we can write n raised to 7 is congruent to n mod 7 here. A raised to corollary what I have written, a is a prime number, then a raised to p is congruent to a mod p. According to that, 7 is a prime, so you can write n raised to 7 is congruent to n mod 7, or n raised to 7 minus n is divisible by 7, because n raised to minus n minus 7 minus n, n raised to 7 minus n is congruent to 0 mod 7. Therefore, n raised to 7 minus n is divisible by 7. Also, n raised to 7 minus n is equal to, we can take n as a common, so remaining n raised to 6 minus 1. N raised to 6 minus 1 is what? N cube whole square minus 1 square. Then a square minus b square formula you have to apply. So writing n cube minus 1 and n cube plus 1. Again, n cube minus 1. Here n minus 1, n into n, this n as it is. Next, n cube minus 1 is what? You have to apply the formula. That is, I will take n minus 1, n square plus n plus 1. That is a cube minus b cube and a cube plus b cube. Both the formulas you have to apply here. A cube minus b cube is equal to a minus b, a square plus b square plus 1, and this a cube plus b cube formula. Both the formula you have to apply. So you are getting here, this term is equal to n minus 1, n into n plus 1, n square plus n plus 1, n square minus n plus 1. Here n minus 1, n and n plus 1 is a product of 3 consecutive integers. See, this is n minus 1, n into n plus 1. It is a product of 3 consecutive integers, hence it is divisible by 3 factorial, that is 6. Now, so as this term is divisible by 6, that is multiple of 6 it is, so hence entire term is divisible by 6 itself. Therefore, n raised to 7 minus n is divisible by 6. Now by using equation 1 and 2, n raised to 7 is minus n is divisible by 7, and n raised to 7 minus n is divisible by 6. So by these two we can write n raised to n minus n raised to 7 minus n is divisible by 7 into 6, that is 42. So n raised to 7 minus n is divisible by 42 here. Next comes Euler's pi function, that will continue in next video.